I am Saurabh Srivastav. I hope all of you are doing well and keeping good health. So I am going to take lectures for your course MTS 201 Multivariable Calculus. And because the class size is large, so live classes are not going to be possible. So what we are going to do is we are going to pre-record these lectures and share with you. And what I will do is, along with the lectures, I will also send you the lecture notes. Okay, the content which I am presenting is also going to be shared with you in a PDF file, so that whenever you need, you can print. And then along with this also there are going to be a tutorial sheet. So these tutorial sheets are going to be important because you look at the lecture and read the lecture notes and try to see what are the points which are not clear. So you go to the tutorials, which are going to be live interactions. So there you can discuss with us in a smaller group all your doubts about the lectures, about the problems which we will give you. And on top of that, we will have an extra session also every week, which we will call office hour or interactive session. There also you can do the same. Okay, and that will be again live, because that will be in a smaller group. So we can sort out any problem that you may have. All right. So just few words about the grading policy. So you must have received an email from the academic office about that, and this grading policy has been decided by the institute for all the courses. So we will follow that word by word, and everything will be written in the document which I share with you, that how we are going to follow that. And all the details about the syllabus as well as the reference book, which is going to be Multivariable Calculus by James Stewart. So I will follow this book linearly, just to make sure that all of you can have the access to the book, and there is absolutely no doubt, because if I jump from one book to another, you may not be able to follow it. So for that reason, I have just decided to follow just one book and write each and everything in the lecture note, which I will discuss over here. Okay, so I hope all of you will take try your best and take the best out of this course. Okay, so our goal in this course is exactly learn the basics of this course, the main ideas in this course. Okay, so that you can use them in your further courses in mathematics, physics, or elsewhere. Okay, all right. So in your first year, if you recall, what you did, you had two maths courses. One was the calculus first course, and then the second course was linear algebra. Okay, in your calculus course, you studied the real number system. You studied its analytic properties through functions which were defined on real numbers and taking values in the real numbers. And then if you recall, you had all these properties, the limits and the continuity and then differentiability, and then you moved on to the integration theory, correct? So one of the theorem over there was the fundamental theorem of calculus, for example. Okay, so these were the main results. So we will require some of these concepts, some of the ideas in this course, and I am sure that whenever there is a need, you can go back and refer to those things, and also I will try to recall in the course. All right. And in your linear algebra, you have already seen the notion of vectors, dimensions, and so on. Okay, so here the treatment of vectors is going to be different. It's going to be analytic. In the linear algebra part, it was mostly algebraic. Okay, so we will slowly develop the notion of vectors. Okay, so in today's class, what I am going to do is I am briefly going to recall some notions which you already know, and then introduce the notion of vectors. Okay, so as you see that I will also discuss the Cartesian coordinate system, just to set the notations, because you already know what is Cartesian coordinate system, correct? All right. So okay, let's move on to the next slide. Okay, Cartesian coordinates. So what is R3 here, we will also refer to as space. So R, we are going to use the notation to denote the real numbers. Okay, this is the same notation which was used in your calculus 1 course also. Okay, and Cartesian product you already know. So basically you take sets and then take their product, correct? So here what we are going to do is we are going to take Cartesian product of R with itself 2 times 3 times. So here I have written 3 times, which is going to be written as R3, and it is what? It is basically the set which consists of these triplets. These triplets are ordered. Okay, this is very important because if I change x and y, this refers to a different point. So these are going to be x comma y comma z, where x, y and z, they are all real numbers. Okay, so this is also called the 3-dimensional space. Okay, so what happens that what we need, in basically we need I mean, look at this picture. What we have these 3 directions. I have only written like half of the direction. These directions will extend the other side also. Okay, so what we have a point which is the reference point O. Okay, this is called the origin. So imagine your room and think of a corner. Okay, and then the point where all the 3 walls meet, think of that as the origin. Okay, so now any point in your room can be described by this way. Okay, that we can say that you move x units in the direction of x, and then y units in the direction of y, and then z units in the direction of z, and you reach that point. And this process is reversible. Like I take any point in the space or in your room, and then you know that you can get what is x, what is y with this reference point. Okay, so this is how we are going to denote any point in space. Okay, now this is very important. The notion of this notion is very important because once I fix the reference point, which is the origin here, and this process basically tells us that I can describe any position of anything. Okay, so for example, if you are sitting in your hostel, you want to describe how to reach the cafe coffee day in the campus. You know that how much you need to move in the forward direction, and then whether you need to take a right turn or left turn. So this is what we are doing over here. Okay, of course you won't see the vertical direction because we are going to be on the plane. Okay, so which you can think of as x comma y coordinates. All right. Okay, so in R3 we are going to discuss several things. Okay, we are going to discuss various geometric features, various geometric objects. Okay, so like equations of lines, equations of planes, and then some quadratic surfaces, which are going to be like, you know, some surfaces in R3, and then tangents and so on. But we will not do it today because what we will do is we will require some extra information, okay, or the notion of vectors. Okay, so the idea is that along with the coordinate system, we also understand what is the notion of vectors, and then discuss all these geometric features in the language of vectors as well as in the coordinate system. Okay, so that is the idea, so that we don't have to repeat the same thing from one language to another one. Okay, so today I'm mostly going to focus just a brief about the coordinate system. Mostly these notations you already know. Okay, so let me just recall another couple of things from the Cartesian coordinates. Okay, so I just have written here some examples. You imagine the plane which is R2, like y equal to 0, so this is nothing but your x-axis, and y equal to x. So this is the line which is the diagonal line, and then y equal to x square. You can also think of the circle and so on, correct? So in R2, you know, whatever geometric figure I draw on paper, that is what is R2, and I can see all its feature mostly, correct, because it's drawn on the paper. But when we move to R3, what's going to happen? We are not going to see its feature on the paper. Okay, so we will require more visualization. We will have to visualize that, you know, what we are going to talk about and what we are seeing, what we are discussing. Okay, so for example, this is kind of a definition, the surface in R3. Okay, so in R2, as I said, anything which we draw, it's called a curve. But when we move to R3, so you take any equation in 3 variables x, y and z, this is going to represent some geometric feature in R3. Okay, and that is going to be referred as a surface in R3. Okay, so we will be able to discuss only some simple geometric features, because any equation, when I say, it can be any arbitrary thing. Okay, so let us think of some examples. So for example, when I say z equals to 3, okay, so look at the picture also. So what does it mean, z equal to 3? What I am saying is there is no condition on x, y, there is only a condition on z. So you go to the height z equal to 3, and at that height look at all the points possible, x, y and z equal to 3. Okay, so this is exactly going to give you this plane. Okay, this plane, only finite part of it is drawn, because any x and any y is possible. Okay, and similarly, when I say x square plus y square equals to 1 along with z equal to 3. Okay, so x square and y square equal to 1. Now there is no z in this particular relation. So what is it? X square plus y square equal to 1. This is going to give you a circle. Okay, but circle, there is also a condition on z, so the circle is only at the height z equal to 3. Okay, so what we have these two relations here, that x square plus y square equals to 1 and z equals to 3. So z equals to 3 is going to decide the z coordinate, and x square plus y square equals to 1 is basically telling us a relation in the x and y coordinates. Okay, so this circle is at the height z equal to 3. In the next example, I have removed z equals to 3. Okay, so now what you are going to see is, you are going to see the same circle at every height. Okay, again, this picture is not drawn completely, because it's not possible. So it extends in both the directions, the vertical and the downward. Okay, so what we have in this, the z equal to 3 is removed, so the condition of z is removed. So that means I am going to have the same circle at every height. So this is going to look like a pipe, okay, which is hollow. What do you call it? A cylinder also, correct? Okay, so now we move on, and just recall that how do we compute the distance between 2 points. So when you did it in the calculus, what was it? You start at point A and then move to the point B. So this was, you were moving along a line. Okay, so the distance was nothing but the end point minus the initial point. So this was B minus A. Okay, but now when we are in dimension 2 or dimension 3, we are not just moving in one direction, we are also moving other coordinates. So this notion of distance is natural. It's also called the Euclidean distance. So what you do is, you take 2 points in the space and say that they have the coordinates x1, y1, z1 and x2, y2, z2. Okay, like this is the first point, this is the second point. Okay, so the distance between these 2 points, we will always denote this by the d of p1 comma p2, or sometimes you will also see in the book they use this vertical lines p1 p2. So this is called the mod of p1 p2, or the distance between p1 and p2. And what is it? What you do is, you take the difference of the corresponding coordinates, like first coordinate with the first coordinate, and then take the square, you do the same, sum them up, take the square root. Okay, so this is the distance between p1 and p2. And in particular, if I take one of the point to be the origin, which is 0, 0, 0, so I get the distance between 0 and p, where here p is x, y, z, is just the square root of sum of squares of the coordinates. Okay, so this is natural notion of distance, and it is also called the Euclidean distance. Okay, now once I know the notion of distance, I can talk about whether the 2 points are close to each other or they are far apart, so this will be used to discuss the analytic properties, because when I say that something is close or something is far, that is going to give rise to the concept of limit. Okay, but that is going to come later only. Okay, but very important, once we have this definition, some important properties can be easily deduced. So for example, if I have 2 points, okay, if the points are distinct, the distance between them is always going to be positive, correct? Because one of the difference will be non-zero, so it will be something positive. So basically the first quantity is saying that only, that the distance between 2 points is 0 if and only if the points are same. Okay, that is the only possibility. And symmetry is also like this, is very intuitive, like the distance between P1 and P2 or P2 or P1 is exactly the same, correct? So that is what this is saying. And the third one is again, this is basically a geometric feature. So it says that you take any 3 points, P1, P2 and P3, then the distance between 2 points you take, so which way I'm saying P1 and P2, it is always going to be less than equal to the sum of the distances between the other 2 pairs. Okay, so P1 P3 and P3 P1, P3 and P2. Okay, so this how do you do it? What you have to do is basically draw 3 points. Okay, I'm not going to give you the full proof of this in today's class. I will give the proof in later on, but this is extremely easy. So you take 3 points. Okay, now what is the possibility when you draw 3 points in this space? There are going to be 2 possibilities. One, that all these 3 points they form a line. Okay, so that means there's going to be a P1 and then P2 and then P3, correct? So in that case you see that this relation will hold. Okay, and in fact you should also see what extra holds here. Okay, and the other case will be when these 3 points are not on the same line. So then when you join these 3 points with each other, what you get a triangle. So this inequality is exactly telling you what you already know, that the sum of 2 sides in a triangle is always larger than or equal to the other side, correct? So this is why it is called a triangle inequality. Okay, so think of the proof, write the coordinates and write the formula for distance, try to prove it. It's just a small exercise. Okay, so this immediately you can define what is a sphere. Okay, so in dimension 2 the analog was the circle. Okay, so you have a fixed point, and then what you are talking about, the points which are at the same distance from that given point. Okay, so same thing you can do over here. So what you do, you fix a point which we will call as the center. So take the coordinates as h, k, l, and take a number r, which is the radius. So what you do is you look at all the points in the space x, y, z, such that their distance with the center is exactly r. Okay, so what you are basically seeing, you are fixing a point in this space, and then you are looking all the points in this space which are at distance r from this point. Okay, so if you collect all such points, that thing is called the sphere. Okay, try to visualize it. And what you have basically, so this is going to also tell you that what is the equation, the distance between C and P, what is it? It is nothing but this quantity, but with a square root. So when I have this side r, I basically take the squares on both sides, so I get exactly this. So sphere is nothing but a collection of points x, y, z satisfying this equation, and when you expand the square, you actually get this equation. Okay, so this is the general form of equation of sphere. All right, so whenever you see an equation which is a quadratic equation, because x and y and z, they have power 2, and remember that they have the same coefficients. Okay, this is very important. So any equation which is in this form with different values of k, l and h, is always going to refer to a sphere in R3. Okay, so for example, if I give you this particular one, x square plus y square plus z square minus 2x minus 4y minus 2z plus 5 equal to 0. So how do you basically see that which sphere it is? So when I say which sphere, what you need to know? You need to know the center, and you need to know the radius, correct? So what you have to do is you try to express it in this form. So what you do is you complete the collect the terms which has x and then complete the square. Similarly do with y and z, and you exactly get this form. So in this particular example, you are going to see the center is nothing but 1 comma 2 comma 1 and r equal to 1. Okay, so these are the notions which you have already seen in your other courses, I'm sure. If not, don't worry about it. We will come back to the geometric features in R3 in much more details, okay, in possibly in 4th lecture. Okay, so